नहीं नहीं 820 से
Sir, am I audible? Sir, am I audible?
Bharat sir, audible? Good afternoon, participants. Welcome to the day 2 of the workshop. So we have two sessions today. Okay, one from me only. Okay, so I'm going to talk about the CMOS scaling and recent trends. And after my lecture, there is one more session by Dr. Bharat Chaudhary on spice modeling. Okay. So hope it is audible to all of these students and participants. You can write if it is audible, then you can write in the chat box.
It's fine. It's working fine.
Bharat sir, I'm going to continue. Can you
Yes, yes,
switch off your
yes,
mic?
sir. You may continue. You continue, sir.
Thank you. So, participants, we are going to talk about the CMOS scaling. Okay, I'll start with the CMOS scaling and the techniques of the CMOS scaling and what are the advancement has been done in the scaling and what are the recent trends in this particular lecture. Okay. So these are my outlines of presentation. So I'll be brief about the CMOS scaling, Moore's law, what was the classical scaling techniques that is called the Denard law, and the process evolution over the period of time, and what is the fundamental limit of scaling. All those things we'll discuss one by one. Okay. So I'll start with the beginning of the computer era. You can see some of the pictures here. So beginning of the computer era started with the vacuum tubes. Okay. So vacuum tubes will form a first computer of this world that is called ENIAC. ENIAC. This is the first electronic computer. Okay. Based on the vacuum tubes. Now you can see how much complex it was when it was introduced first time. So by the end of this, in 1956, the ENIAC contains 20,000 vacuum tubes, 7,200 point contact diodes, 1,500 relays, 70,000 resistors, 10,000 capacitors, and consume 15 kilowatt of electricity. So you can see there is a huge requirement at that time. If you compare the things with today's generation, you will see everyone is using the mobile phone that is containing a very strong processor, right? So if you compare with this first electronic computer, so you realize that at that time how it was very difficult, but nowadays it is very easy, and we are using i9 processor in our computer systems, i7 processors, right? And based on the FinFET technologies we are using the processor. But these are the some glimpse I'm going to show uh, from the starting of the computer era. So before Moore's law, okay. So before Moore's law, the computer systems were basically not the computer system. The integrated circuit, if you talk about the integrated circuit, is made up of bipolar junction transistor (BJT). Okay. So this BJT, as you all knows, that it was not suitable for the digital applications. We always study MOSFET is better than BJT, right? So initially, when William Shockley developed this BJT, okay, and when Moore's law was not into the picture, so BJT was used to making the integrated circuits. So, but the problem is, you know, that the BJT is a not bilateral in nature. Okay, it has a emitter and collector. Those are not exchangeable, unlike the MOSFET, where source and drain that can be exchangeable very easily. That's why it's make a realization of integrated circuit is easier in MOS devices. So you can see this is the first integrated circuit chip. Okay, it in earlier 1960s. It was ECL, three input gate by Motorola in 1966 by using the Bell Laboratories. Okay, and it was used the BJT as a component for making the integrated circuits. But when you go to the next generation, we are all are using PMOS or NMOS kind of architecture. So I'll going the brief about the PMOS technology. This Intel first processor, Intel first processor, that is 4004 processor, that is a 4-bit processor, was developed because of the introduction of the MOS technology. Okay, so especially it is designed on the micrometer PMOS technology, as you can see from the slides. And data bus width, as I told, it is 4-bit. Number of transistors, very very important. It was around 2300 number of transistors in early 1970s. So when you go further improvement, now Pentium 4 processor. Okay, it started in 2005, and how many transistors was there at that time? That is 125 millions of transistors in the Pentium 4 processor. Okay, and the die area was 112 millimeter square. Okay, data bus, very very important. Data bus width is 32 bit at this time. Okay, and the supply voltage was 1.2 volt only, and it is based on the technology that is called the CMOS technology that we learn in our curriculums, that is 90 nanometer CMOS technology. Okay, again, if you go further uh, over the evolution over the period of time, so from one core processor to we move to the two core processor or more number of core processors, where the important thing is that transistor number of transistors. You can see earlier it was very few, now millions, now it is going to a 291 millions. Okay, and it is based on the 65 nanometer multi-core processor, 65 nanometer technology. I hope you are aware of different technologies. Okay, so that is possible. Why this evolution over the period of time is possible? Because of the only one parameter, that is called the CMOS scaling, and CMOS scaling is driven by the Moore's law. Okay, so Moore's law. What do you mean by Moore's law? Basically, Gordon Moore, he was one of the scientist working for the Intel, he basically published one paper in early 1970s, and based on the trends of the integrated circuit, he predicted that every 18 to 24 months the number of transistors will get doubled in an integrated circuit. So he was predicted at that time, but manufacturing companies, those are working in those domains like Intel, they have actually followed this principle or follows this guideline. So that will over the period of time it will named as Moore's law. Okay, so Moore's law is the first major shift in the past 50 years, representing the economic standpoint, because when you go from one technology to another technology, there are various advantages. In terms of most advantage in terms of economics, we are getting the the cost of fabrication of per transistor. If you talk about the cost of fabrication of per transistor in terms of dollars, it is going to reduce in each technology generation. From it is just a show. Here you can see this. I have shown it some pictures from starting from 180 nanometer technology to 130 nanometer technology, where you can see the earlier number of transistors in 180 nanometer technology in 2002 was 2.6 million number of transistors. Now, if you go from a 2004, after approximately 2 years, so 130 nanometer technology of CMOS will be used using the 4.4 million number of transistors. Again, if you go further, 2006, 2008, 2010, up to and so on, you can see that number of transistors are increasing exponentially. Okay, but after 2012, when we reach to the 28 nanometer technology, we are getting not that much of increase. Okay, so this that's why they predicted that we are going towards saturation of the Moore's law. Okay, we'll see that whether it is feasible or not. Okay, so 28 nanometer technology, where 20 millions of um, transistors were there. Okay, and still some of the companies those are working in this area. Okay, so they are increasing the number of transistors, but they are optimizing the process and how these things can be improved further. So this change in the technology over the period of time leads to some remarkable change in the business industries like manufacturing industries. If you talk about the semiconductor manufacturing industries, from 2001, you can see there are list of companies. There are the big list of the companies those are working for the semiconductor technology. But over the period of time, you can see the number of companies, like there are 10 to 12 companies was there in 2001. Now they are reducing in number. Why it is happening? Why it is happening? Because when you go for a skilling, we required a very accurate process. For accurate process, we required such kind of instruments, okay, so that it can manufacture a nano level of design, and that instruments are very costly in nature. They are only be considered by when we're talking about semiconductor manufacturing company. Those manufacturing company will update their technologies of the fabrication. Okay, so because of these dimensions were very low in nature, some of the companies find that they are very expensive in nature. If you go for fabrication of very small uh, transistors around 20, 22 nanometer, some of the companies thinks that they are not feasible to cope up with this requirement. So they have merged their business with another companies. Like you can see, for example, IBM. Most of the faculty members or students those are attending the workshop, they might be aware of the company IBM. IBM, we know that is for software, but they are in business of hardware. earlier. Okay, so they had the IBM laptops. You might be aware of that. IBMs are that they're having their own laptops they're selling, but we don't see any kind of IBM laptops nowadays. Why? Because IBM was not able to sustain their business or sustain their manufacturing plants for semiconductor industry. So that's why they go down, right? So that's why they merge their business with the another company. So I'll give example. The IBM has merged their business with the global foundries, right? You can see this global foundries chart in 2005, but there is no IBM in the list in 2015. Sorry. So 2015, only four major key players: Intel, Samsung, TSMC, and global foundries. So these are the major role key players in the semiconductor industry. Most of the hardwares designed in the based on the 14 nanometer and 16 nanometer technology, they were from these companies. Okay, so this that's why there is a lot of challenges in scaling of the transistors, and they are facing a lot of difficulties, right? So if you want to understand the scaling, okay, so these are the some pictures I'm going to show. Okay, so we move from the 180 nanometer, 120. Sorry, this is not 120. This is 130 technology. 1 minute, please. Sorry for the disturbance. CMOS 130 nanometer technology. So CMOS 130 nanometer technology is changing from 130 to 190 nanometer technology, and then 90 nanometer to 65 nanometer technology, right? So these are the some change uh, happened over the period of time. So most of the students might be aware about this change. So actually, if we talk about the Moore's law, so if we go from one technology to another technology, how this number can be decided? Anybody can say that how this number can be decided from 130, why it is only 90, why it is not 75, and so on. So the main reason is that we're talking about the length, okay? And the Moore's law said Moore's law depends on the so area will be go down. Suppose A1 is there, so if we go from one technology to another technology, the area two should be area 1/2, right? So this is the Moore's law for the period of 18 to 24 months, right? So if we talk about 130 nanometer technology we have, if we scale the 130 nanometer by root 2, okay, if we talk about length by root 2, approximately we'll get the 90 nanometer. So similarly, if we width are also reduced in same fashion, so L into W divided by root 2 and root 2, that means it will lead to area by 2, right? So that's why these things are there in place of a integrated circuit. 1 minute, please. Sorry for the disturbance, some urgent work. So this will leads to a change in the technology by area by 2. So that's why this number comes in the picture. Now see the animation that if you are moving from 130 nanometer to 32 nanometer technology, okay, how many number of cores that can be fit based on the 32 nanometer that is equivalent to 130 nanometer. Okay, so if you see there are yeah, if it is one chip like this, so total 16 number of chips can be fit if we compare between the 32 nanometer technology to the 130 nanometer technology. So you can see the scaling means keeping uh, dimensions small for a transistors, so that we can uh, increase number of transistors in a integrated circuit. So more number of transistors will leads to more number of functions or more powerful processor, or in terms of memory, the more number of memories can be integrated on a same chip. Okay, so these are the some pictures again. This is the actual pictures how transistor can look like in a nano dimensions. This is, if you go from 130 nanometer to 90 nanometer to 65 nanometer up to and so on. Okay, so basically, if you summarize that Moore's law, you can see the number of transistors will increase. Okay, you can see the trend. Their yellow line will show the increase, and the price per transistor goes down. That will all about the Moore's law. Okay, so how basically scaling will impact on the overall performance. So we say that in theoretically that if we go for a scaling of a dimensions, like let's say how much scaling is required, what parameters are going to scale. So that will given by the concept that is called the classical scaling, that is given by the Reynolds law. Okay, and this is the basic structure of a MOS. You can see. So there are having in MOSFET, we have the source terminal, we have the drain terminal, and we have the gate, and we have SiO2 layer, SiO2 layer that is having the some thickness of POX. This is called the effective length. Okay, and substrate having some doping. So these are the and junction depth is called the junction depth that will form a reverse bias junction between P terminal and N terminal. So this is the basic structure of a MOSFET. If you see that what are the parameters are going to scale when you talk about the scaling technique. So these are the device dimensions. Device dimension include length, width, and outside thickness. Okay, and if it is considered as some scaling factor, if you are going to scale with a certain number, let's say we have gone to that 1 by k, that should be equal to 1 by root 2. That means this k is approximately root 2 for over the period of time when we talk about the scaling. Okay, and the doping concentration is increased. Okay, if you go from one technology to another technology, so root 2 times your doping concentration needs to be included. Otherwise, there will be a problem of in these junctions. Okay, and it will leads to a higher leakage current. So voltage, similarly, another parameters are voltage, current, capacitance. Okay, these are the basic parameters. Okay, so based on these parameters, this performance can be judged. These are the three performance parameters. As you can see, delay. So delay depends on the simple delay equations is nothing. Tau is equal to RC, time constant. RC is proportional to nothing but V by I, R, and C is load capacity. So for if we talking about only one transistor, so if we reduce the size of a one transistor, what will be the change in the delay time of a circuit if we are made from the same transistor? Okay, so if delay time will be equal to 1 by k times, that means how much it will change? That will reduce by root 2 times. This delay will be reduced by 1 by root 2 times. That means we are increasing the performance or speed of operation by root 2 times. Okay. So second, power dissipation circuits. So power dissipation will depends on the V into I, voltage and current. So if voltage are reduced by 1 by K times and kappa times, sometimes called kappa, okay, it is written by 1 by kappa square. Okay. So you can see if kappa is equal to root 2, that means power dissipation is going to reduce by half P square. Okay. So if we talk about 180 nanometer technology to next technology 130 nanometer technology. So in 180 nanometer technology, let's say the power dissipation was 50 microwatt. So if we talk about 130 nanometer technology, then the new power will be 50 by 2 microwatt. That means it should be 25 microwatt for same operation or for the switching, for the same switching, right? In an integrated circuit. Similarly, another parameter is called power density. So power density is written by power divided by area. So if area is reduced by 1 by k square and the power is reduced by 1 k square, so it will cancel out, the power density will remain same. Okay. So classical scaling was described in 1974. It was a very long story, right? So because of that, we are getting continuous improvement in terms of performance because of the scale. And this picture shows this MOSFET morphology, that how it looked like in case of a uh, design. If you talk about the layout, so we have a layout session tomorrow at 10 o'clock. So all the participants should attend this session, how to design a good layout for integrated circuits. So these are the pictures I am showing, and this zoomed version will show the very small dimensions that will show the effective length between the MOSFETs. Okay, source to drain, this is called effective length. Okay. So you can see metal oxide, how metal oxide can be visualized. That we see very SEM images, TM images, that's commonly used for taking pictures and showing into the their research outcomes. So this is the some pictures. Okay. So now learn about the basic of the MOSFET. Now you can see what is the purpose of MOSFET in a digital integrated circuit. The basic question, because we are not dealing with the MOSFET, we are dealing with the processors, okay, memory. So they are basically actual applications. So in the actual application, what is the role of a MOSFET inside the application? So their role is just that they are acting like a gate. Okay, they are acting like a switch, ideal switch. So if we talk about ideal switch, this is the characteristics of an ideal switch. So if we take a threshold voltage, this is considered to be a threshold voltage. Okay, but if we this is considered to be a off-state leakage current when no gate voltage is applied. Okay, and this is considered to be on current when voltage applied is equal to power supply voltage. Okay, and if we talk about the MOSFET switch, how it is different from the ideal switch, MOSFET switch uh, will function as what's this log? This C. So this graph is represented in terms of log ID, right? So it's not ID. Remember this log ID. So if we keep increasing, the log ID increases in order. Okay, let's say this point is having some current. This is 10 to the power minus 9 ampere. So we can say the off, this is off stage current. So we can say the off state current of a transistor is equal to 10 to the power minus 9 ampere. Okay. And this is considered to be on current. So ideally the current order should be in terms of 10 to the power 3 or you can say milliamperes. Okay, 1 milliampere. So this way you can analyze away any MOSFET. So for a digital application, on state current and off state current both are very important. So in MOSFET, if you talk about, there are three main parameters. One is called the threshold voltage, one is called the IM current, and another is the field current. Okay. So this is again a MOSFET physics operation, how the MOSFET will operate from off condition to on state condition. Now, this is the diagram we have seen. ground state current, there are N plus P and N plus region and outside. So there, when gate voltage is equal to 0, if you want to draw some band diagram for a conventional MOSFET technology, you can see that this is a band diagram that will show a change here because it is a P-type doping concentration and it is an N-type doping concentration. So band diagram has been drawn in the inversion layer at this particular point. Okay, so this will show a barrier. That will create a barrier. But that is why this is energy band diagram. This barrier will be responsible for creation of the threshold. If the barrier is reduced to zero, that means there is no barrier, means we have overcome the threshold voltage by applying the suitable gate voltage. If we apply some voltage here, so this band is going towards down because we are making the P channel into the N channel by the phenomena of inversion. So this second picture will show the how current actually flow in case of a MOSFET. Now you can see when we apply the voltage at this terminal and gate and drain terminal, the channel will be formed like this, especially in case of this on state condition. On state condition, MOSFET will generally operate in the saturation region, right? As you might be aware, these are the simple concept. Okay, so I'm not going into details of how the cutoff in linear and saturation, those we already know. Okay, so in case of a saturation region, there will be a current flow possible from the source to a drain, electrons flow possible. So how this electron will flow? Because of the this dotted line you can see. This flows the electron flow. Okay. So you can see, you can relate within the previous, there is a barrier. Now there is no barrier because we have applied the gate equal to VDD voltage. Okay. So because of that, the band diagram changes in such a way that there will be no barrier between the source and channel. Then source can send the number of electrons very easily and they can be turned into the drain. So that's why the electrons flows from the source to drain over the period of certain time. Electrons are considered to be charged, right? And if it is Q by T is basic current, right? So this is the basic mechanism of MOSFET to current flow. Okay. If we talk about the threshold voltage depends on the three factors. How any threshold voltage of MOSFET can be decided. It depends on the flat band voltage, depends on the Q depletion, because there are depletion region present here. It will form Q depletion region, oxide capacitances, and the this is called the uh, inversion. Because of the inversion, we need to apply such a voltage that this should be equal to 2 pi f. Okay, so this 2 pi f, pi f is the potential barrier. Okay? And if we apply a voltage such a way that it will got inverted, so that's why pi f and pi f equal to pi f. Earlier it was P, you can say it is N. If you change the semiconductor from P to N, then it is required a this much of potential barrier change. So that's why this equation is defined for the threshold voltage. Okay. So this how it depends. So basically, VFB depends on the gate material, what kind of different materials we are using in a MOSFET architecture, and oxide thickness, second parameter, oxide thickness, if it is large, then the VDF will become large, right? So this way, and Q depletion, whether doping, it depends on the doping concentration of the channel. The doping concentration generally it is considered to be low doped, order of 10 to the power 15 to 10 to the power 16. Okay, and last that is about the change in the potential barrier, applied voltage. Okay, so these three parameters are required. Okay, so for forming a threshold voltage. So now we have the simple current equation. You can see this is a on-state current in MOSFET that can be realized by simple ID is equal to Q by T and electric field VD S by L, velocity UV, and the time, if you using three equation, the time will be equal to L square mu into VDS. And this inversion charge equation, half of the source side, half of the drain side. This way we can get the equations here, and the total equation if we solve, the conventional equation of a MOSFET is given by mu and C of mu is equal to by VGS minus VGS into VGS into VGS square. This is the conventional MOSFET equation for any device. So if we talk about the off current equation, what is the equation for the off current in case of it? Because in the MOSFET, this is the very very important. ID VGS characteristics are very very important. Okay. So if we talk about the how this current is decided below threshold region, because we have derived the current equation that is valid for above threshold. Okay. If we use the previous equation, if then if we below threshold voltage, the current will be equal to zero. But actually, the current is not equal to zero. Okay, there are some current flow because of the diffusion of the carriers and thermodynamic emission. You can see this about showing that Vg is less than Vth. Okay, this is thermodynamic emission and diffusion. Okay, so because this barrier is very high, so there is very high. How we can represent the current equation? By this way. IDS is it an exponential function of VGS minus VT? You can see log ID, and this is VGS. So if we take a exponential with both log and both sides, it will become log ID, and this will become a VGS. So log ID and VGS have a very linear relationship from this particular off state, zero state to VTH state. Okay, and further on there will be a small change. Okay, because the drain current is also a function of drain voltage. Because when we apply at the drain terminal, a small voltage will apply the carrier concentration in the drain and source will change, and that will form a again a diffusion process. Because of the diffusion process, the current is going to change. Okay, and there is one more important factor, that is called sub-threshold swing. Okay, sub-threshold swing is decided by this parameter 1 by S. Okay, S is the slope of this graph, and S is the 1 by S. Sub-threshold swing is 1 by S. So, sub-threshold swing will decide that how much fast a MOSFET can switch from off state to on state. Okay, so that can be derived from the log ID versus VGS characteristics only. Okay, if we are designing a MOSFET that will give a lower value of sub-threshold swing, the ideal value of sub-threshold swing, we know that that is equal to approximately 60 millivolt. Okay, that came from this particular equation. Okay, if you use this equation, we will get this because I of depends on the this particular equation. Sorry, this equation will get this substitution is equal to 60 millivolts per decade. Okay, so why I am telling all these things, because when we talk about the CMOS scaling, if you go for CMOS scaling, if the large transistors are there and small transistors there, if large transistor is there, there will be certain VTH, and a small transistor is there, their VTH will going to decrease. So you can see this animation. So in this case, there will be a small VTH will be there in smaller device. So because of that smaller VTH, there will be change in the sub-threshold swing. Okay, sub-threshold swing. 1 minute. So this to show that when we are scaling the device, the leakage current is going to increase. Okay, that is a problem of CMOS scaling, we can say. Okay, so this decade will change will show. So if we talk about the scaling of MOSFET, the important parameter is that is we know that from the previous slide the leakage current will increase. But what are the different leakage current is possible in a MOSFET? You can see so there are three components that will cause a leakage current in MOSFET. One is called the gate leakage current. That gate leakage current arises because of the thinning of the oxide thickness. Okay, so when oxide thickness is small, there will be a large electric field exist between the this gate terminal and the body terminal. So because of that, there will be possibility of tunneling of, because we are talking about nanoscale dimension, right? So if you are nanoscale dimension, so if we talk about the electric field 1 volt only, 1 volt, let's say, and if the dimension is 10 nanometer, so see how much electric field is there? 1 volt divided by 10 nanometer, right? So then, so ultimately it will comes to megavolt per centimeter, right? So megavolt per centimeter is very huge number, right? So because of that, tunneling of carriers is possible, and this tunneling of carrier will lead to a gate leakage current in a MOSFET. Second is important, channel leakage. The channel leakage is because as we discussed, VTH and S depend. It is depend on the VTH and swing, the IDVGS characteristics dependence. Okay. Third parameter is junction leakage current, and junction leakage is doping dependence. Junction leak, that's why we have to increase the doping when we talk about the scaling by factor kappa. Okay, and this leakage current possible because of the formation of vertical P junction diode. This is the N terminal and P terminal. So that will form a vertical PN diode that will match this possible, because when we apply a drain voltage of plus 5 volt, let's say, and we have a substrate connected to 0. So this is nothing but a reverse bias PN junction. And there's reverse bias PN junction, as you know that there will be a small reverse saturation current flow in case of a PN junction. Okay. So the points to be remembered in case of a MOSFET for controlling VTH and IO. That is very, very essential when we talk about the small technology. So increased doping so that junction leakage and uh, eye of power will affect it. Okay. Second, scaling junctions. So the cons of the scaling junction is that the series resistance will increase, and it will lead to a ion reduction. If we talk about series resistance will increase, obviously the ion current will reduce. The third point is scaling TX. So because of the scaling TX, leakage current will reduce, and it will lead to a higher I of current. Okay, so all are correlated together, and poly depletion effect occurs when we talk about the scaling of the MOSFET. Okay, and because the poly depletion is nothing but a from the silicon, and we require some doping. So because of the poly depletion effect, that will limits the scaling technology, and that will reduce the ion current. Okay, and then further points are reduced VDD. Reduced VDD will leads to a ion reduction. These are the factors come into the picture when we talk about the MOS transistors. Okay, and we have to take care of all these parameters when we go for a scaling of a MOSFET. Okay, and these are the different applications, you know, that over the period of time has been observed by the different electronic gadgets that will based on the CMOS technology. Okay, mobile phone, TVs, computers, and all. Right. So now we move from the CMOS technology to complementary CMOS technology. As you know that the complementary CMOS is a combination of pull-up network and pull-down network, right? Because when you move from the NMOS to CMOS, then any circuit realization is possible. Okay, and NMOS is acting as a pull-up network, as pull-up pull-down network, and PMOS pull-up network that will make it useful. This can be a series and parallel combination of the technology. I'm not going to detail. This is the fabrication structure, right? So this is the cross layout, and how many different layers are involved in case of a CMOS inverter, as you can see here. So we required a P plus diffusion, we required N diffusion, the polysilicon, metal, and SiO2. So these are the basic thing you need to remember as a student, that these are the essential parameters required for a CMOS devices. So if we want to fabricate this CMOS devices, how many different mask layer will be required? So we basically, if we read the CMOS fabrication process, so there are 6 steps required. Okay, one is for formation of the well, then formation of the polysilicon layer. So for formation of the polysilicon layer, we require a masking. So this layers basically cross section. This is considered top layer. This is a top. Okay, so top view. So top view will define the mask, what are the different masks required for the fabrication of the CMOS. Okay, so this can be acted as one layer. This for different contact. This is for basically contact. These masks are shown for the contact formations. Okay, similarly, some masks required for the pre-well and annual creations. So this will make the complete CMOS inverter like that. Okay, with combination of N P plus, P plus, and interconnection between the two devices, NMOS and PMOS. Okay. So what can we do for a retrieve a healthy scaling? Okay. So this for a healthy scaling we have to use this kind of concept. Okay. So for the oxide scaling there should be a proper sense between the oxide and length. There should be no we cannot decide the number randomly. Okay. And junction leakage, to avoid the junction leakage, these are the pictures I am showing that some of the different research papers have shown that this should be the proper things, the proper dimension you should use to avoid the any kind of further short channel effect. Okay, so short channel effect is we discussed earlier. The most common in case of a scaling of a device is leakage current. So to avoid those reduction in the leakage current, these are the philosophies has been explored in the literature of MOSFET. Okay, substantial control will be required. A VTH and VDD should be in the range of 1 to 5. Doping increase के लिए हमें क्या करना चाहिए 1/3 का रेशियो रखना चाहिए to make a DIBL free architecture. Okay, less gate poly depletion effect को avoid करने के लिए हमको POX by L should be in the ratio of 1/30 divided by 40. Okay. So these are the things. So when we go for a process evaluation over the period of time, the CMOS is no more now. If we talk about the current technology, okay, now we have complete the CMOS scaling process. Now we are going beyond the CMOS process. Okay. So if we go beyond the CMOS process, you will find out that it 32 nanometer technology, there is a one concept called FinFET come into the picture. Okay, so we have, I'm giving just a brief overview. Okay, and FinFET in detail will be taught by Dr. Rajesh. Okay, so earlier, what is the difference between earlier scaling and now scaling? Okay, earlier scaling is given by the cost. Okay, given by the performance. Performance constraints are there. Active power dominates. But nowadays, if you talk about earlier, means we are talking about scaling in microns. Now means we are talking about the scaling in nano dimensions. Okay, nano scale. So scaling drives the down the cost. We still agree, but not that much as we find out in earlier. Okay, so but now material device, the different kind of materials are being used, like compound semiconductor materials, like, and the combination of silicon germanium, that is compound semiconductor material strain technology. So these are the different techniques to improve the performance of a FinFET design or CMOS design in nanoscale dimension. The power constraints, because as we discussed that standby power dominates nowadays because of the further scaling. So that's why it is essential to cope up and rectify these kind of requirements. And collaborative design approach means basically companies, as I told, that they are not able to design independent things. Nowadays, they are collaborating with each other. Okay. So in summary, we can see that when we go for a technology scaling, the speed or CV by delay will reduce. Delay will reduce by around 100 times, 10 times, but the off leakage current goes around 100 times, increase in the leakage current because of the scaling technique. So, possible solution, right? What is the possible solution? Possible CMOS scaling solution. The possible scale solutions are the strained silicon. So strained silicon is a mechanical method where we have to strain the silicon in such a way that the mobility will increase. In traditional CMOS scaling, as we find out that we have to increase the doping by k times. If we are increasing the doping by k times, then what will happen? If we are increasing the doping by k times, then uh, your mobility is going to down because mobility is inversely proportional to the doping. So because of that, another type of concept that is called strain technology will use so that by using the strain technique, the mobility of the transistor will increase. Okay. And another technique is called high K technology, right? So high K technology is come into the picture when the gate leakage current was very, very high. When the gate leakage current was very, very high, and that is possible because of the using a small silicon dioxide. So when we are using a small silicon dioxide, the gate leakage current will be high. When we go further down, there will be a huge problem with higher gate leakage current. So because of that, they move from the traditional SiO2 technology to called the high K gate technology. What do you mean by high K here? High K is meant for high dielectric constant material. Okay, generally in MOSFET we use SiO2 material, but here we use silicon high K dielectric HFO2 kind of things. For example, I will give you example of HFO2. HFO2 is one high K dielectric. Al2O3 is one high dielectric. Its dielectric constant is around 22. Al23 is around 12. Okay, so HFO2 dielectric constant, and if you compare with the conventional SiO2 dielectric constant, that is equal to 3.9. Okay. So you are getting over 5 times change in the high K dielectric. Because of the relative dielectric constant is higher, it will limit the flow of gate leakage current. Because gate leakage current depends on the thickness of the dielectric. Okay, so if we are using because we talked about the capacitance, right? Capacitance scales. At what factors capacitance scales by the TOX. Okay, so in the if we take is equal to max C1 is equal to C2, we have to epsilon R not into TOX, right? Epsilon R not epsilon R divided by TOX2. Okay. So for making the same capacitance, since the dielectric constant is higher in this case, okay, 5 times, so we can increase the if it is 5 times increase, so we can here we can increase 5 times here, right? So that's why we'll give a relaxation that we should avoid we should make a higher thickness of dielectric. So if we are using higher thickness of dielectric, then leakage current will proportionally decrease. So this is the major rate change at 45 nanometer technology while introduction of the high K metal gate technology. Another major change is tri-gate architecture. The tri-gate architecture is advancement to the CMOS technology. So tri-gate architecture like FinFET, okay, FinFET or you can say sometimes called multi-gate transistors or double gate transistors. So the double gate transistors. So this is a tri-gate. So FinFET and tri-gates are almost similar. Okay, and Intel, if you talk about the Intel, they are currently working on the this tri-gate architecture only. Right now, we are using 10 nanometer tri-gate Intel FinFET in our new laptop and new processors and new laptops, right? Especially those are Intel-based processors. Now, this will come into the picture from 2009 onwards. then introduction of the 32 nanometer technology. आप यहाँ पर देख सकते हैं this 32 nanometer technology के बाद से 12 nanometer up and so on बढ़ता गया. So in 2020 we have 10 nanometer technology we are using it, and 2021 it is expected that 7 nanometer technology will come up with Intel. Intel is working in the 7 nanometer technology. Okay. So what do you mean by this 3D? Right, 3D, yeah, different tri-gate architecture. I was discussing. So tri-gate, there are different kind of architecture has been explored in the literature. In case of a over the period of time, the FinFET is generally considered to be a fin kind of a. Why it is called FinFET, not the CMOS or something? Is because it seems like a fin of a fish. That's why it is called that is called it is called FinFET architecture, right? So because of the FinFET, you can see here there is a double gate architecture, gate one here and gate one gate two here. Okay. In tri-gate, we have all around gate one, gate two, gate three, and all are connected together. So similarly, different architectures has been proposed in literature. The most famous architecture is FinFET and tri-gate. Tri-gate, why tri-gate? Because Intel is working on the tri-gate. And FinFET, like TSMC, I showed the list of the company, TSMC. TSMC especially work on the FinFET architectures. Okay. So why this different devices has been explored? Because the performance has to be improved, right? So if you compare the different designs, like this is a tri-gate, HK means high K metal gate, strain technology, and classical. So you can see that it smaller technology node, it 20 nanometer technology, 22 nanometer technology. Which one is having the higher performance? Tri-gate. So tri-gate will have the higher performance in 22 nanometer technology is compared to any other technology. Okay, so that's why they are famous now, and we are using. So if we are using any mobile phone, okay, and just go and see this after the class that there is a specification of the mobile phone. In specification, you especially focus on the processor. Your processor, you'll find out that it is based on the FinFET technology that we are talking about, right? And they are basically mostly based on the 14 nanometer or 10 nanometer CMOS. So I'm talking about the latest one. Okay. So these are the comparison earlier drawn from 90 nanometer technology to 65, 45, 32. ये सारी चीजें compare की है. So especially at 32 nanometer and below, FinFET technology is more popular. In 45 and 32, we can say the high K metal gate technology was popular, and before that, 90 and 65, CMOS technology, classical CMOS technology was sufficient to use. Okay, and these are some pictures of the tri-gate Intel technology introduced in 2011. Okay, and this you can see some pictures. This is the 32 nanometer planar transistor and 22 nanometer tri-gate transistors. जो दो अलग-अलग. तो tri-gate और planar में क्या difference है आप देख सकते हैं with this picture. Okay, so tri-gate is sometimes also called the 3D transistor. This is also called the 3D transistor. Okay, what about the performance? Okay, so where the non-planar can go? The non-planar can go up to uh, ultra thin body devices to FinFET devices to nanowire transistor. So in some of the lectures, I think this is more advancement. Nanowire transistors are advanced than the FinFET technologies. They are under in research itself. Nanowire transistors and FinFET transistors are in production. Now you can see this performance of these all these is denoted in terms of two factors. SS, that's called subthreshold swing, and second is called the DIB, drain induced barrier value. This is the one of the parameter when we go for a scaling for measurement of a digital performance. Okay. If DIBL is low, that means it is a good device. If subthreshold swing is low or it's reaching towards a 60 milliwatt per decade, then this particular is a good device. Okay, so as we can see from the observation by different research group, okay, IEDM is shown here. IEDM is a very good conference in US, and it will happen in December every year, and there are participation from the different industries those are working in this domain. They particularly focus on this conference and what are the innovations they are doing in this field. They demonstrate their, so in 2010 itself they demonstrated that the nanowire transistors are the future of the electronic industry. Okay. So this is a big list, like, okay, so end of the domain and start of the domain. You can see here. This is end of the domain and start of the domain. This table basically shown by the ITRS. It's called International Technology Roadmap of Semiconductors. Okay. So they have International Technology Award is ITRS, International Technology Roadmap of Semiconductor. This is a international organization who predict that what will be the future after 10 years. So it is, you can see that after 2024, they are moving from a 3D the vertical gate 3D transistor like nanowire architectures. They are coming into the domain and expected to fulfill their requirement up to 2000 to 2030. Okay. So earlier we have the FinFET architecture because the FinFET is the current trend now. That's why it is highlighted here. Okay. You can see this. These different parameters are there. You see, there are a lot of parameters are there, right? This is related to one MOSFET. Imagine these parameters are related to the MOSFET only. FinFET height, pin height, pin width. Okay, in CMOS we don't have the concept of so much. Pin width, pin height. What do you mean by pin width and pin height? So because they are in 3D nature, the height that means the pin height, where the fit is prepared. A width is means pin width. Okay, so these are the different dimensions are. So if you are to detail of this, you go to the ITRS website, International Technology Roadmap of Semiconductor. So those are working in this domain, especially those are doing MTech projects or a PhD project. They must go visit this website and find out what is the next generation electronics and what are the next generation semiconductor devices. For if you are working in this domain, it will help to identify you the correct topic and what topic you are going to do research or what topic you are going to do a presentation. Okay, these are again from ITRS. So this is a big list. Okay, so how long Moore's law can go? Like as we have seen that the trends of the CMOS technology is expected by 2021 will be having a 3.5 nanometer devices. Okay, and ITRS start production that you can see it is goes up to 2030. Okay, so currently we are in 7 nanometer and less than that. Expected to we are reaching the target early than the ITRS production. Okay, because of the hard work of the semiconductor manufacturing company. So expected that up to 2030 it might go, and after that most long may end. Okay, so for again there are certain devices that can be used for further elaboration like nanowire design, that is the 3D design. Okay, those kind of thing will come over the period of time. Okay, to maintain the concept of Moore's law so that we can get the better performance. All those things are going for low cost and better. The purpose of the scaling is just to reduce the economics, reduce the cost of the electronic devices. Why we are studying this? Because these are the already development happened over the period of time, and we found that Intel develops manages to improve the performance from the one technology to another technology. Okay, and tri-gate transistor is the current trend now. Okay, and that is has the major advancement over the CMOS technology. And fundamental limit says that it will go up to 3.8 nanometer or 4 nanometer of design. And below that, there will be possibility that silicon lost their nature, like another type of nature will come into the flow, जिसको बोलते हैं wave nature and all, that will coming into the picture. Okay, so that's why this can be end of the scaling possibly 4 nanometer. Okay. So this was my last slide. Okay. So these are the some reference I used for making the slides. Okay. I will stop the video. Okay. If you record it. If a student, if any questions from the student side, Bharat sir, are you here?
Yes, sir, I am here. Am I audible, sir? Yes.
Yeah, audible. Which questions?
No, sir, nobody has posted yet, but again, I am requesting to post that questions in the chat box.
Yeah. Student, if you have any query, you can post it here. So it will be interactive if you ask questions, right? Seems attendees are 28 attendees and nobody is asking questions. Means, or maybe you are aware of all those things. I assume that you all are aware of these things. Okay, so slowly we are moving towards some advanced topic that will help you for your dissertation and thesis work. So I have gone through this. I have not gone through with very detail. I have just gone through the overall summary that how the picture is changing and how the CMOS is moving towards a new generation of electronics. Like, please tell about triple whale technology over twin whale technology. Triple whale technology. Okay. So basically, in FinFET designs, I'm not go into details of the twin tap technology. Is know that there is a conventional CMOS technology where we form a twin tap process. Okay, that you are asking. Okay. So, Winter, you might be, sir, is there any possibility of development of triple gate structure after MOSFET? Possibility means it is in already it is in market, na? Sorry, triple gate. This FinFET they are in market. They are we are using their applications like in processors, in memory. Okay, and you are talking about tunnel FET, right? I have not talked to tunnel FET. Tunnel FET is something different. Okay, some of the researchers say that this can be a future of FinFET. Okay, because tunnel FET works on the different concept of there is tunnel FET. So we are going to cover tunnel FET in the 4th day of the workshop. So this, yeah, triple gate. So tunnel FET can be a single gate, double gate, triple gate. All kind of architectures has been explored in the literature.
Sir, one additional question from this from Shibani Mishra. That what is the link you said those who are doing their project they should go through? What is the link? So they are asking about the link.
The link, okay.
Okay.
Link as IT, as you search the in Google, ITRS. ITRS, they say that is called International Technology Roadmap of Semiconductor. There is a website of ITRS. Okay, where you will find out what are the latest development in this area. Okay, and what will be the future after 10 years. Like one person asking about the tunnel FET, right? So in ITRS, you will find out that researcher over the world has showed that tunnel FET can be one of the good device in future. So that's why people are working in tunnel FET. Even some of the MTech and PhDs, those are working in this area. They are doing research in this domain. So not in India, it is all around the world. Okay. So in India, as we know that we have the limitation of manufacturing facility. In India, if we talk about where the manufacturing facility is available, so we have very limited places like SCL Chandigarh. You heard about SCL Chandigarh? In SCL Chandigarh, they are working especially for the ISRO because they are the unit of ISRO and they are working on a 180 nanometer CMOS technologies. But we have discussed here for FinFET technologies, but FinFET technology, can we basically fabricate FinFET technology here in India? Okay. Yes, we can, but there should be facility should be available, right? So one more thing is that ISC Bangalore and IIT Bombay have the good fabrication facility. Okay, they have the very good fabrication facility, and if some of you are interested in this area, you can write one project to the IIT Bombay and ISC Bangalore for fabrication of FinFET, right? So under the INUP program, if you are aware, INUP is Indian Nano User Program. So this INUP programs, uh, we can basically they ask for a proposal. When you submit your proposal, okay, then if they find your design, because before the fabrication you have to do certain simulations, right? So that's why in earlier previous day we talked about the TCAD simulation, right? So TCAD simulation is a device simulation tool, okay, where you can actually design this kind of devices, FinFET devices or tunnel FET devices or thin film transistors, any kind of semiconductor devices, small in size, okay, you can design and simulate. Simulation means the prediction of the results, I mean how performance, prediction of the performance, how it will perform. So if your design seems good and like, then you can go for a fabrication. And for a PhD or MTech, for a MTech is expected that you should do the some simulation work in some of the BTech students, you do some simulation work, you should learn the TCAD tool, okay, you take any one of the design like FinFET or tunnel fit, whatever is for your suggested by your supervisor, then thoroughly simulate those things. You implement, try to read more number of research paper. You implement some of the design available in the research paper. You try to replicate those results, okay, using the simulation, okay, and if you find out satisfactorily that you are able to implement work, then you read some more paper and you find out that how we can improve the performance of this particular design. Then you do some modification in the there are a lot of engineering is possible, gate engineering, source engineering, channel engineering, right? Change in some doping concentration. The first thing all, before going into the new design, you should understand the basics first, okay? So and that's why we recommend to learn TCAD, because when you design by yourself, you understand the concept of CMOS, you understand the concept of doping, you understand the concept of different manufacturing processes like lithography processes, like okay, all those things you learn. And once your learning is over, then you think that what will be the features and how to estimate the performance. Once you able to understand how to estimate the performance, then you can basically uh, try to make a new design by changing in this source contact, drain contact. So because of there are a lot of papers. If you go to IEEE and search for a MOSFET, you'll find out a lot of paper. If you search for a FinFET, you'll find out a lot of papers, right? So there is huge work has been done this area, okay, and so first, I will suggest try to fix only one topic and read those topics thoroughly. So before going into new topics, the CMOS is the basic. You should understand the concept of CMOS first, then you can learn the new things. Okay. Any other query, sir?
No, sir. So far, I think
Got
uh,
what is the major advantage Tri-Gate over FinFET and vice versa, which offer base performance at lower technology? Okay, so good question. FinFET and Tri-Gate actually. So Tri-Gate is and FinFET both are common to the multi-gate technology. Okay, and Tri-Gate is specially focused by the Intel. Intel as working as a manufacturing. FinFET is a kind of double gate architecture. Okay, so if you use double gate architecture, this have the advantage over the single gate architecture. They have advantage. So these things again will be discussed in later classes in detail. What is the advantage? Okay, so here we can see the FinFET multi-gate has different structure, tri-gate as well as double gate. So TSMC manufacture because they have the patent on the double gate technology, and Intel prefers tri-gate technology. Okay, and both are comparable. Both are performance improved is compared to the CMOS technology. So you can do one project on this comparison tri-gate versus technology. Which is better, MOSFET, MODFET, or FinFET technology? Okay. So MOSFET, you know that MOSFET is gone nowadays, right? All are talking about FinFET. MODFET is also old technology. So FinFET technology is better because I told in the slide, FinFET technology starts from 32 nanometer technology and below. And CMOS is in micron, it was in nano also, but up to the 65 nanometer technology. After that, 45 nanometer technology, high K metal gate technology, and below that, 32 nanometer technology and 22 nanometer technology. So FinFET technology is better in terms of performance, and it is leading to a lower cost also, okay, because of the mass production. Okay, I think then no more question. We can stop and we can take some break, and Bharat sir will be ready for the next lecture.
so, sir, I hope that by 4 o'clock we will be there.
Yeah, sure, sure.
So,
We'll take 10 minutes break.
okay.
Then we'll
So,
start
all
the lecture.
so I request you to all participants, please be there around at sharp 4 o'clock, and because it will be too late to complete in the evening time. So be there at 4 o'clock. Okay.
Finish around 5 o'clock, up to 5 o'clock.
No, sir.
Bharat sir?
It's around 1 hour and 30 minutes.
Okay.
So it will be 5:30.
5:30.
Okay.
Sir, it is visible.
Okay, sir. Sir, am I audible? Am
Yes,
I
yes,
audible?
audible. Yeah.
Audible. Okay.
Yes, yes, audible, audible. One is asking question. Let me clarify that TFET is better or FinFET. Okay. So TFET has their own advantages and FinFET has their own advantage. So you learn both the things and compare. Right. So TFET is suitable for ultra low power application, but it has meanwhile their advantage because the on current is less in the architectures. Right. So the researchers are doing investigation how this on current can be improved. And compared to FinFET, FinFET is industry trend nowadays, right? And it is in applications. But it is expected that we'll move from FinFET to tunnel FET or any other architecture in future, like nanowire architecture. There is many alternative to FinFET design. So one of the alternative is tunnel FET design. Okay. So now you can continue, sir. Thank you.
Okay. Thank you very much, Chitrakan sir. So, good afternoon to all the participants. So, about the next session, we will discuss on CMOS logic design and its challenges. So, this will be that very fundamental lecture for, especially for, it will be a learning experience for the undergraduate students. Because I will explain about that basic CMOS digital logic designs and all. Thereafter, if time will permit that, I will explore that fundamental circuits in the spice modeling, and we will do circuit simulation as well. So let's start with the CMOS logic design. So, as you all are aware, that CMOS stands for the complementary metal oxide semiconductor, where that complementary term uh, 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 is maybe due to that there are that two different type of transistor. One is N type and another is P type, and these are in complementary in nature. And this especially the one N-type transistor electrons are the charge carriers, whereas in the P-type holes are the charge carriers. So electrons are the free carriers in the conduction band with that energy of conduction band as EC or just above the conduction band edge. And free electrons are generated by doping the silicon with N-type impurities such as arsenic or phosphorus and arsenic. These are the basically fifth group element. If we dope such type of materials into fourth group element like silicon, germanium, so we will be able to generate such type of semiconductor which are called N-type. And whereas in case of P-type semiconductor, the third group elements like boron, aluminium, gallium, indium, thallium are doped. So such type of material are called P-type material, and where hole is the charge carrier, and this is the vacancy of an electron in a covalent bond state. That means missing an electron which would otherwise be part of a silicon to silicon bond, and holes are free carriers in the valence band, and these lies with the energy of EV. EV is that valence band energy or just below the valence band edge. It depends on that doping concentration as well as that variation in the temperature. So where that Fermi level lies, so it may be at valence band or just above or just below the valence band. second term is that metal that here that transistor gate is made up of aluminum metal. It was in the earlier days it was made up of aluminum, but nowadays it is being made of polysilicon. And next is oxide. That silicon dioxide is the material between gate and channel. This is that most preferred material and will work as an insulator between metal and semiconductor. And semiconductor that here that you all are aware that silicon is that most it is the most regularly used semiconductor in such type of devices. Is the type 4 element in the periodic chart. Each silicon atom bonds to four other silicon atoms in the tetrahedral crystal structure, as you all studied in your earlier classes of engineering. So now that what that CMOS comprised of two type of structure, NMOS and PMOS. As you all are aware that in the NMOS device that there is a P-type substrate is there, whereas in case of the P-type devices here the P-type of substrate will be used. Whereas in case of N-type NMOS that channel is N-type, whereas in case of PMOS that it is made up of a P-type. And here that source and drain terminals are doped with N type of impurities, whereas in case of PMOS these are doped with a P type of impurities. And here that positive voltage is applied to the gate potential, whereas in case of the PMOS here that negative voltage is applied, and there is a direction of electron flow from source to drain. Here that electron will flow from drain to source. So here what is the basic as you are aware that fundamentally that if we are applying that positive voltage in the NMOS means we are applying gate potential high, so relative to source that will turn the device on, whereas in comparison to NMOS, in the PMOS if we are applying low gate voltage means that will allow the transistor to be on. So these are the complementary in nature. And here 0 volts in case of NMOS, 0 volt will turns off the device. Similarly here if we are applying 1, then it will turn off the device PMOS transistor. So now we are moving towards that CMOS circuit. So CMOS is made of that combination of NMOS and PMOS transistors. That's why it is called the complementary MOS circuit. So this is the most fundamental circuit and the basics fundamental circuit in the digital design. So the here that drain terminals are connected, both NMOS and PMOS drain terminals are connected to each other, whereas that PMOS source and substrate terminals are connected to higher potential or the power supply. These are connected to higher potential to eliminate that body bias effects. Similarly, for NMOS transistors, these source and substrate terminals are connected to that lowest supply. That means here that ground is the zero potential, so this is also connected to ground because there is a requirement to eliminate this body bias effect. So here these NMOS and PMOS are connected to each other, and this we already studied. And here if we are applying V input is high, V input is high means that NMOS will on and this VDD will off, this PMOS will off. That means whatever we are applying at input, that this NMOS will on means that V out will be directly connected to ground. That means V out will be 0. If we are applying high, then we are getting low at output. So this will function as a inverter. So now if we are applying a low supply voltage at gate terminal means this NMOS transistor will be in cutoff mode and PMOS will be on. So there is a that means output will be directly connected to the power supply, means we are getting high high logic at the output stage if we are applying low at the gate terminal. So this is that basic functionality of CMOS inverter, as you all are aware, and this is the schematic representation or the inverter symbol of CMOS inverter. Now this transmission gate, this is that uh, one kind of gate that is made up of CMOS transistors. Here this is the combination of NMOS and PMOS transistor. When we are applying, we input at that source source terminals of both the transistors. Here N and P devices with source and drains are connected in parallel, and VG is that the control voltage. Here we are applying VG, and here we are applying the complement of VG. So this is called the control signal. So when VG is high means at VDD, so and VG complement is therefore low, so that means that NMOS and PMOS are both are on. So depending on the device's potential, one may be on more strongly than the other. So switch is therefore closed, and V out will be the same as that logic V in. So when VG is low, if the gate voltage is low, means we are putting at ground potential. Then VG complement is high. That means both the devices are off. So switch is therefore open, and V out will be independent of V in. So this is also called the high impedance stage. So whatever that in the earlier stage, that will be replicated to the output stage. So this is also called the tri-state or high impedance state. Now that moving towards the basic fundamental gates, here two-way NAND gate. Now here we can simply classify this NMOS combination circuit is a pull down structure, and this PMOS combination circuit is called a pull up circuit. So now that this T1 and T2 transistors are the NMOS transistors and connected in series, whereas T3 and T4 are the PMOS transistor, which are connected in the parallel with their sources at VDD and their drains at V out. So operation, if both A and B are high, both A and B are high means VDD. So these two transistor T1 and T2 are on, means that therefore pulling V out low, means these are on, means that V out directly connected to ground, means we are getting low at output. So if both T3 and T4 are off due to their gate to source voltage, now if either A or B both are low, means at 0 volts, or either transistor 1 and transistor 2 both are off, that means T3 and T4 are on. So thus output will be pulling to power supply, means V out will be high. So this is the fundamental gate. NAND gate is there, and this is the symbolic representation of NAND gate. So we will be able to make this gate from that basic CMOS circuit. So this is the two-way NAND gate. Now similarly, this is the two-way NOR. This is the opposite to NAND, means in the pull down network there is this parallel combination of transistor T1 and T2, whereas in case of NAND gate, this is the series combination of T1 and T2 was used. So that the working principle is same. So this is the symbolic representation of a NOR gate. So this is the same, and now this is that three-way NAND gate, means that combination of three transistors, and the series combination will be used in the pull down network, whereas that parallel combination will be used in the pull up network. So this is a similar operation like as we have earlier discussed in the previous slide. Now that compound logic means it is the combination of that logic, means sometimes it may be multiplication and sometimes it may be that summation of that variables. So here the series combination in the pull down network means there that AND operation, and that the parallel combination means that there is a OR operation. So here we are applying A and be at T1, T2 means A and B are multiplied, whereas C and D are multiplied, and both are in the parallel structure. So this is that sum of these products. And as you are all are aware that V output will give that complement to that whatever we are applying at that pull down network. So this is that output logic in any fundamental, in any compound logic where T1, T2 and T3 are connected in the such combination. Now we will discuss about that XOR gate. So XOR gate here, as we discussed in the previous slide, these are connected in series combination. So A into B, and this complement of A and B are applied to transistor T3 and T4. So that series combination will be given as expression A bar into B bar, and there is a parallel combination of T1, T2 and T3, T4, and this will give that OR operation, and finally it will be complemented at the output because these are connected in the pull down network. So this is all about that CMOS circuit operations in 4 different gates. So similarly, we can design that multiplexer by using CMOS circuits. Here, there the combination of PMOS and NMOS transistors are used, and these are the select lines, and these are the inputs. So whatever the we are getting at Z, that is called output. So we can design 4x1 mux by using CMOS circuit. So here, if we are applying S naught is S naught is low. S naught is low means these PMOS, this will be on, and similarly this is connected to these two will be on. Similarly, if S naught is high means these are connected. This is connected to S naught is high means S naught bar is low. S naught bar is low means this circuit will pass on A, and similarly if this is S naught bar is low means if S naught is high, that means this will pass on A and C. So this is the fundamental operation of 4x1 multiplexer, where we are using 12 transmission gates, 2 inverters for select lines. Now similarly, SRAM cell, here 4 NMOS transistors and 2 PMOS transistors. Here there are the 2 PMOS transistor T5 and T6, and 4 NMOS transistor T1 to T4 are used. Here T1 and T2 called active devices, and T3 and T4 are called the input output devices, where T5 and T6 are called loads. So the cell, this SRAM cell is comprised of 2 cross coupled inverters, means positive feedback. The 2 vertical lines, bit lines, means B0 and B1, are used for sensing state of cell and writing data in the cell. So these are the actually bit lines. So these are used for different operations, writing and reading. So one horizontal line means word line. This WL is used to select a row of cells for writing and reading, and to prevent that unselected rows of cells from being disrupted. So the circuit operation, so when cell has two stable states, 0 or 1. When 0 is there means node X0 high and node X1 is low. This will be high and this will be the low state. So means T2 and T5 are on, and T1 and T6 are off. Similarly, for one state, node X1 will be on, and this X1 will be high and X0 will be low. Means that will be the opposite situation. Means T1 and T6 are on, and T2 and T5 are off. So means no DC current flows in either of state. So means in the read operation, raise WL to VDD and pull one bit line high and pull the other bit line low. Similarly, for write operation, that we have to raise that WL line to VDD, whereas we have to precharge bit lines to half of the VDD. So this is all about the read write operation in the SRAM cell. Now that we may as far as we discussed about that how that we will be able to implement that the basic fundamental gates from CMOS logic circuits. So now similarly we can implement that combinations of such gates, means the combinational circuits. So now this this flip-flop is actually a sequential circuits, whereas that the combination circuit, this there is a combination, means latch is the basically combinational circuit. So that uh, we will be also be able to implement latches by using the CMOS logic circuits. So here the circuit schematic is comprised of two D latches. One is that positive latch and another is negative latch. Here the two D latches tied in series combination with input D and output Q. Q is there. One is actually, this one is that master latch, and this one is the slave latch. So whatever is being applied to that this master latch, it is being followed by the slave. So it depends on that data input, whatever the data input and the situation of the clock, how that clock will pass on the data to that slave stage. So each D latch is simply constructed out of the two inverter cross coupled with a transmission gate. Here they said that there is a transmission gate is there, and in the feedback loop having a second transmission gate, this one in series with the input. Each transmission gate switch C is closed if its control input is high and open if its control is low. So single clock fed directly to second latch and inverted to first latch. So operation, this actually this will this is actually positive as triggered, means there is a rise, there is a change in the data with the positive rise of that clock pulse. So when clock goes to 0, master latch is opened. This will be the open to D input, means feedback loop is disabled. This will be the disabled while slave latch holds the previous data and close to signal at the load QM. So similarly for that, when clock goes to VDD, this master latch is isolated. Now in this case, that master latch is isolated means that whatever that at the output stage will at the master stage will directly reflect to the slave stage, means that input D to hold the data while slave latch opens to receive data from master, giving valid Q output. So this is all about that operation of that positive as triggered register, or some it is also called flip flop. Now that now we will discuss about that basic structures made up of CMOS design. So there are that complementary logics and standard CMOS, as we discussed already discussed, clocked CMOS, BiCMOS, and there are that some ratioed circuit logics are there: pseudo NMOS, saturated NMOS load, saturated PMOS load, depletion NMOS load, source follower, and additionally further there are the dynamic logic circuits. These are based on the these are working in the different principles: CMOS domino logic, NP domino, NORA, cascade, voltage switch logic, sample set differential logic, and pass transistor logic. So we will discuss one by one. So now this is CMOS complementary logic. As we discussed, this is the basic fundamental inverter, and this is two input NAND gate. This is actually this two input NAND gate. There is the series combination of A and B. This is that, and we are getting the complement of A into B bar here. And this is actually two input NOR gate. And now this is the actually complex logic gate, where there is a combination of A into B plus C and plus D into E, and it will give the output will give the complement of this complete expression. showing position of poly gates by ordering of device inputs. So each logic function is depicted for both pull down and pull up logic tree. So pull down tree gives that zero entries of the truth table, that means implement that negative of the given function. So as we are these we have already discussed, and what are the advantage of such type of CMOS logic is that low power high noise margin design case. It is easy to design, and functionality is also simple. And what are the disadvantages? Higher input capacitance is which will reduce that ultimate performance. Means these parasitics and capacitance will affect that performance of that logic circuit, and this will contribute that additional power consumption and delay in the circuit. So these are the limitations of CMOS, and we will also discuss that further limitation of such designs in that subsequent slides. And this is the AND or inverter CMOS gate. AND or inverter complex CMOS gates can be used to directly implement a sum of product Boolean function. And this pull down AND tree can be implemented as follows. So this is basically these are the ended operation of A1, A2, A3 and P1 into B2, B2, C1, C2, C3, and parallel combination will give that OR operation. So this is AND or invert CMOS gate. So in the pull down network, whatever we are getting that logical expression that can be complemented, finally that will be complemented to give that exact expression. So product term is series connected NMOS transistor. Some are denoted by the parallel connected gates, and that complete function must be inverted representation as we discussed. Now see this over and inverter. This is opposite to that previous one, and over inverter. Here that parallel combinations are connected in series. So they're the parallel combinations of A1, A2, A3. It means these are the A1 plus A2 plus A3 into B1 plus B2 into C1. So finally we are getting complement of this expression at means that will be the final expression. So this is all about AND or inverter and OR and inverter. Now this pseudo NMOS logic. This is that pseudo NMOS is a ratio circuit actually. A ratio circuit means that sizing parameters of PMOS and NMOS are dependent to each other. So there is some ratio, specific ratio of W by L that will decide the logic. So where DC current flows when the N pull down tree is conductive. So it must design the ratio of N devices of W by L to P load device. So W by, so that when N-type pull down a leg with maximum resistance is conducting, means that output is at a sufficiently low level, means VOL. So for the logic shown in that diagram A, the devices D and E would have a W by L roughly 6 times higher than the P load. So here this these are the different W by L ratios for the different NMOS transistors, and an alternative approach is shown in B, means provides a bias voltage V bias somewhat about the ground, and the P is the pull up loads. So allow the P load devices ratio to set equal to the N device ratio for gate arrays, and another application where devices operations are limited. So now next is complementary pass logic. Complementary pass logic means here we are utilizing the CMOS transmission gate and just the single polarity version of transmission gate to perform any logical function. So logic inputs may be applied to both the devices gates, both the device gates as well as the device source and drain. So as earlier we in case of transmission gate, that logic this controlling signal was applied at that gate potential only, whereas in case of that complementary pass transistor logic, this variable function can be applied at source and drain terminal as well. So only limited number of pass gates may be linked in series before a clocked pull-up. So what is the main advantage? Means there is the less requirement of number of gates. So here this expression, when A is high, if A is high and A is high means that A is high means that B is passed through the gate of the to the output, and if A is low means B bar will be passed through the gate. So this is that simply shows that XNOR circuit including a cross coupled input with a P pull-up device which does not require inverted inputs. Here we are implementing XNOR gate, whereas there is no requirement of inverted variable function. So simply we can implement XNOR gate by using A and B only. So there is no requirement to complement these variable functions. So this is because we are applying these A and B to the gate as well as source and drain potential. So this source and drain potential, if we are applying that logic variable, so we can implement that whatever that desired function. So this is all about that complementary pass transistor logic. Now next moving towards CMOS transmission gate, as we already discussed about the such gates, and we are taking just an example of two input mux. Now if S is here, S is the select line. If S is low means this transmission gate will on. That means it will pass on this. It will pass that input A. And if S is high means this transmission gate will be on. So S is high means it will be complemented. Here it will be low, and this transmission gate will be on means that directly B will be connected to output, means B will pass on. So this is the basic functionality of 2x1 mux. Similarly, XOR can be implemented by using this such CMOS transmission gates. Here this top circuit implements an XOR function with the two CMOS transmission gates and the two inverters, by using two inverters. So here this is that 8 transistors total. How these are 8 means here there are the combination of PMOS and NMOS, and one inverter is made up of two transistor PMOS and NMOS. So there are total 4 transistors, and there are the 4 transistors, 8 transistors total. Whereas these can be reduced by 6 transistors by eliminating one transmission gate. So by using only one transmission gate, this XOR gate can be implemented. So this is all about that how we can optimize that circuitry by using different combinations of transmission gates and CMOS inverter. Now this CMOS pass transistor logic, as we already discussed, here we are applying that variable inputs as at terminal as well as source and drain terminals. Now if A is applied at this source terminal of the NMOS transistor, and this A and B will pass on this, and it will be inverted, then this will be that we are getting A into B bar. Similarly, if A bar and B bar are the inputs to the inverter, and we are getting that inverted output, means that complement of A bar into B bar, that the A into B. Similarly, there is that we can we will be able to get A into B bar plus B into B. So B into B means plus B, A into B bar, and this will give the complement. So we can solidify that by using De Morgan's theorem. So we will finally get A plus B bar means NOR operation, and similarly this will give A bar into B bar plus B bar into B. This B bar into B will be 0, and A bar into B bar complement, that finally complement will give A plus B. So this is all about that CMOS pass transistor logic, and there the basically we have implemented NAND and NOR gates. Here this is the NOR and this is the NAND gate. Now this we have already discussed about that combinational gates. Now we are moving towards that sequential logic, sequential CMOS and NMOS logic circuits. So sequential logic circuits contain one or more combinational logic blocks along with memory in a feedback loop. So basically sequential circuit will differ from combinational circuit because these are using additional element that is called memory. The next state of the machine depends on the present state and that inputs. So how this memory will play that important role in that circuits, and this output depends on the present state of the machine and perhaps also on the inputs. So there are basically two types of machine cycles. One is the Mealy and the second one is the Moore machine. In the Mealy machine cycle, this output depends on the state of the machine, whereas in case of the Moore machine, that output depends on both the present state and the input. So what are the topics we will cover in this section? SR latch, JK latch, D latch, flip-flop, clock, CMOS, and clock distribution logic. I think you already discussed such type of digital logics in your earlier classes of undergraduate engineering. But we will discuss such circuits with CMOS design. Now this is cut. You as you all are aware, this SR latch. This is the NOR gate operation. Now there's a NOR based SR latch contains the basic memory cell. Actually, memory cell means there the feedback of output and the feedback of complement is to be applied to that another NOR gate. And these are the back-to-back inverter gates are there built into in NOR gates to allow setting the state of the latch. So set goes high, M1 is turned on. This will be turned on and forcing Q to low, and which in turn on pulls Q to high. So when set is 1 means we are getting output as a 1, and if reset goes high means M4 is turned on and Q is pulled low, that means it will be pulled high, and this Q bar complement is pulled high means if reset is equal to 1 means Q complement will be high, and so if both set and reset are low, both M1 and M4 are off, and the latch holds in the existing state in indefinitely period. And if both set and reset go high, both Q and Q complement are put low, means giving an indefinite state, because this is not actually valid state. This one, it is not allowed because Q and Q bar Q complement cannot be same. They should be opposite to each other. So this stage is not allowed. So the gate level symbol and truth table for the NOR, as you all are aware about that, this is that if we both are low means that we are getting that hold operation means previous stage, and if set is 1 means we are getting the output as set, and reset is 1 means it will be the reset to previous state. So this is the fundamental operation of CMOS SR latch by using NOR gate version, and similarly this can be expressed by NAND latch as well. And now this is the shown at left is that the NOR based SR latch with a clock added. Here we are applying the clock signal, so the latch is responsive to inputs S and R only when clock is high, and when clock is low, that means that latch retains the current state. And this is the timing diagram waveform. This the level sensitive nature of the clock SR latch means when S goes high. S goes high means during positive clock, and leading clock edge means that rising edge after changing in S and R during clock low time, positive glitch. Here we are getting that glitch in the S while clock is high. Here this one is the glitch in that set state, and when R goes high during positive clock. So this is all about this basic fundamental SR latch operation. And now this another one is that clocked CMOS SR latch. How it is implemented using CMOS gates. So this is that we are additionally we are applying clock signal, and this circuit, as you already discussed, as we have already discussed here. So CMOS and or inverter implementation of clock and or based SR latch shown in the left. Only 12 number of transistors required when clock is low. Two series lags and tree are open, and two parallel transistors in P tree are on. Thus the returning state is in the memory cell. And when clock is high, that circuit becomes simply a NOR based CMOS latch. Means it will be the simple SR latch. Similarly, this is the JK latch NAND version. And this SR latch has a problem in that when both S and R are high, means S and R are when both are high means it will give that invalid operation. So to overcome this problem, we are using that JK latch, and if this J and K are 1 means that latch will toggle on the next positive going cycle, positive going clock edge, and this is also one invalid stage to. So to avoid such condition, this is also called race around condition. Means there is the toggling of the stage Q and next stage and previous stage. So to eliminate such condition and to overcome that this disadvantage of JK latch, there's that master slave configuration is used. So this is the master slave flip flop. So by using this master slave configuration, such type of condition will never arise, because we are using that edge triggered clock. So the feedback path occur from Q and Q bar slave outputs to the master input, and that does not exhibit any tendency to oscillate between J and K equal to 1 no matter how long the clock period. So since opposite clock phases activates the master and slave latches separately, means simultaneously, though both will not be on. So the NOR based version can be done with 4 AOI CMOS gates, and it requires 28 number of transistors. So this is all about JK master slave flip flop. Now D-latch implementation, simple. If we are applying simple D input, and it can be made up of CMOS inverter. So a D-latch is implemented at the gate level by simply utilizing NOR based SR latch and connecting D to input S and connecting D to input R with an inverter. When clock goes high, D is transmitted to output Q, and when clock goes low, the latch retains the previous stage. So that's why it is called that transparent latch as also. So, and if D latch is normally implemented with this is called transmission gate switch shown in the left. So by using transmission gates and CMOS inverters, this such type of latch can be implemented. So now if input for transmission gate is activated with clock means if clock is low, this transmission D will be passed on, and if clock will be high means this will be on, means that feedback path will be on, means whatever that we are applied in that input side will be held by that output stage. So let's set with the prior data D. And now this is the alternate CMOS D latch implementation. Here this is that tri-state inverter is used. So this is the alternate circuitry. Here we are using that CMOS D-latch and is implemented with the two tri-state inverters and a normal CMOS inverter. This is actually this is a normal CMOS inverter. These are the tri-state inverters. When that means when clock is low, clock is low means this will be on, and this will be also on, means that output will confuse about that which stage to attain, means either 0 or VDD. So this is called the high impedance state or the tri-state. So that's why these are called tri-state inverters. So when clock is high, the first tri-state inverter sends the inverted input through to the second inverter, while the second tri-state is in the high impedance state. And when clock is low, the first tri-state goes into the high impedance state, and while the second tri-state inverter closes. Here when clock is low means this will be on, and this will be also on, and this will simply work as a simple inverter. Whereas if it will be high, means that this inverter will goes into that high impedance state. So this is all about D latch. Similarly, there are the two D latches are there, negative latch and positive latch. If this the combination of such latches are used, this will work as a resistor. This is called positive edge triggered resistor. That means at positive rise age of the clock, there is a change in that output stage with respect to input data. That's why it is called that positive edge triggered resistor, or it is also called that flip flop. And here that basically we are using single phase, means only clock. If we are using the two phase, means clock and clock bar, this is called the two phase system. And this is the falling edge, and if we are using here using first positive negative latch and positive latch. Here if this that configuration is reversed, then we are getting that falling edge triggered flip flop or resistor. Now this is the we are moving towards that clock to CMOS logic. Clock means we are applying the clock in between the pull up, pull down and pull up network. And this is like that similarly like that tri-state CMOS inverter. That clocked CMOS logic has been used for very low power CMOS and on minimizing hot electron effect problems in NMOS device. And this clocking transistor is high. To maximize or at the power supply end of the logic gets maximum protection from the hot electrons. So these are the circuits which are used for that low power VLSI design. And now this we are moving towards that dynamic logic gates, dynamic logic circuits. So these are actually based on that temporary storage, charge storage across that capacitor. So these are the temporary transients in that output level. In that output levels will remain valid only for a certain period of time. Here static logic gets its output level as long as power is applied. Whereas in case of dynamic logic, if we are removing the power, even after there is a logic level will be maintained across that parasitics or load capacitor. So that will work as a power source. So dynamic logic is normally done with the charging and selectively discharging capacitance. So this charging and discharging is called as pre-charge and evaluate. So pre-charge means clock to charge the capacitance, and evaluate means clock to discharge the capacitance depending on the condition of the logic inputs. So what are the advantage over static logic? if comparing to dynamic logic, means these will avoid the duplicating logic twice as both N tree and P tree as in standard CMOS, and typically can be used in the very high performance applications and very simple sequential memory circuits amenable to synchronous logic. And these are high density achievable, consumes less power. Why? Because there is no requirement of power source as we are withdrawing that power supply. And disadvantage means compared to static logic means there are the problem with clock synchronization and timing, because we are not applying any clock, and it is very difficult to design such type of circuit. Now that the first one, this basic fundamental concept, we will only discuss about fundamental concept of dynamic logic gate. The pass transistor here, the pass transistor MP is an NMOS device, could also be implemented with a transmission gate. Here CX is charge capacitance, represents the equivalent capacitance of the input gate. This is that actually equivalent capacitance of this transistor CG. Actually this can be implemented as CGS, and part of an inverter, as well as the PN junction capacitance of MP's drain. And this is actually equivalent capacitance of both the transistors, and this is called as CX. When the clock CK goes high, means MP, this transistor will be turned on and allows the input voltage V in to be placed on the capacitors, means this capacitor will fully charge. So V in could be high or a low voltage. When clock goes low, means this transistor will be turned off, and trapping the charge on the CX, means the whole charge will be will store across that capacitor CX. And now when operation for a 1 or a 0, if V in is high, means here say VOH, then MP will allow that current to flow into that CX, and this is charging up to the VDDs, means then it will charge up to the maximum power supply, means VDD, and charging it up to VDD minus V threshold, means this there is a drop, or that drop of voltage across that PMOS transistor, that is called VTN. And if V in is low, means this is connected to ground, then MP will allow current to flow out of that CX, means the current will flow in this direction, means this will work like as a source. Means if this is connected to ground terminal, means this will work like as a voltage source. So if MP, this transistor is NMOS, that this capacitor will discharge to the ground, and if this transistor is PMOS, mean this transistor will discharge to the VDD, because if this is the PMOS transistor, these gates, those terminals are connected to the higher potentials. And if this transistor is a transmission gate, and this capacitor could discharge in either direction, means transmission gates means it is made up of the combination of PMOS and NMOS, so it may discharge into that either of the direction, either in the VDD side or ground side. So this is that dynamic CMOS logic gate. In dynamic CMOS logic circuit, actually there's a single clock is used and can be used to accomplish both the pre-charge and evaluation operation. And when this clock is low means this will be on. PMOS will pre-charge the transistor MP. This will be on, and this will charge V out to VDD, since it remains in its linear region during the final pre-charge. And during this time, that logic inputs, when this is the low, means it will pre-charge, output will be high, means this is the condition of pre-charge. Now if this will be that if we are applying that if this clock goes high again, means that MP is turned off, this transistor will turned off, and that NMOS evaluated transistor ME is turned on. And if this will be high, means this will be turned on. The turned on means this whole circuit this logic gate will consume the power from this supply V out. The not supply exactly. This is that capacitor, load capacitor or parasitic capacitances are there across the output. At that time, it will be isolated from the power supply, as that clock is high means this transistor will isolate that this this complete circuitry from this power supply. So this is called that evolution phase. So evolution phase, during the evolution, this circuit operation will be there. A1 into A2 into A3 plus B1 into B2 ka bar will be there at the output. So these are the inputs are such that a conducting path existing between V out and this transistor ME, the V output will finally this V out will discharge to 0. So this is called that evolution phase. So now again for that negative cycle, this when clock goes down, this V out will charge, and this is called the pre-charge stage. So this is the fundamental concept of dynamic CMOS logic gate. And now by using such type of logic gate, we can implement different logical expressions by using that clock. And now this is actually A into B plus C plus D into E. So there is a two transistor PMOS and NMOS are used in pull up and pull down network. And in the pre-charge stage, V out will charge up to the maximum up to the power supply. And during this, if clock goes high, means that it will isolate from the power supply and it will come into the evolute phase. So finally, whatever that logical expression uh, we are introducing in the pull down network will prevail at the output. So this is all about dynamic CMOS logic gates. Now we are, as you all are aware, that in any typical mixed signal system, mixed signal means in that uh, such type of integrated circuits where this analog and digital blocks are integrated at a single circuit. So such type of circuits are called mixed signal systems. So in typical mixed signal systems, this there are basically DSP processors are used, which are using conventional static CMOS logic style. So in typical system, that analog input is used, and it is pre-processed by some filters and analog to digital converters into a digital output. And this digital output will be processed by such DSP processors, where fundamental logic circuits are used, which are CMOS logic style. And after processing this signal, this processed signal will be again converted into the analog version, as we have to replicate, we have to reproduce that our input as a output. So this is all about the typical mixed signal block diagram. So as CMOS logic gates are fundamental logic gates to be used in the integrated circuits or typical mixed signal systems. So, but there are some limitation in such type of logic styles to use. So, as you all are aware that this is the basic fundamental CMOS inverter operation, and there is a large spike in that switching current that is in the range of around 750 microampere. This is that this is the one circuit simulation waveform. So it is in the range of that microampere, and this current is significant if we are using that lower technology nodes, means, and this current is undesirable, and this will contribute to that noise in the circuit. So actually this such type of styles nowadays are not preferred to be used. So there are some alternatives to such type of CMOS logic styles, and there are many alternative logic styles were introduced over the time. and these generate lesser switching noise than classical CMOS logic, and the suitable for integration in mixed mode signal environment as a replacement of a complement of CMOS logic. Such styles are the basically two types of there are basically two types of logic styles: single-ended and double differentially ended. Single-ended means that single-ended input is there and single-ended output is there, whereas the differential-ended logic means differential-ended inputs are there and output may be single-ended or differentially ended. So these there are basically course current steering logic, current balanced logic, positive feedback source coupled logic. In the similarly for differential ended, that different logic styles were introduced over the time. Complementary current balanced logic, folded source coupled logic, current mode logic. Now that most preferred logic style nowadays is the current mode logic style. This is the similar to our differential amplifier, but what is the major difference in that current mode logic inverter? This is the conventional MOS current mode logic inverter. Here that there is a current steering of either this branch or this branch. So this is based on that current steering principle. Whereas in case of differential amplifier, whole current drawn from the power supply is equally divided into both the branches. Whereas in case of CML inverter, it will drawn from either this branch or this branch. Means like this will like a car steering. So there's the actually current steering. This is based on the current steering principle, and this is made up of there are the three networks. This is called pull up. This is the pull down network, and this is called current source. And now the basic characteristics as compared to the CMOS logic style is that the lesser switching current, it is in the range of nano ampere, lower power supply is required. Whereas to operate such a CMOS inverter or this classical CMOS logic gates, there the larger power supply is required, and these will offer the higher speed of operation. Voltage swing is also less. This is that resistance of that these two resistors, or if these can be implemented by using the PMOS inverter, then this resistance is called RP, and ISS is that constant current, and there is a lesser dynamic power distribution. However, this will offer some static power consumption, but that is also very less as compared to the CMOS logic gates. So we have also verified by using different simulations that this is the switching current for CMOS. This is around in the range of this milliampere or microampere, and the thousands of microampere. Whereas in case of current mode logic, this is then the range of few microamperes or in the range of nanoamperes. So this is all about and there are the basically two fundamentals. Different types of CML gates are available. This is the differential inputs. There are the two differential inputs, and we are getting the differential outputs. So if this differential input is high, we are getting that complement at the output, because either of this branch will on, and similarly this we are getting, if we are applying that single-ended input, we are getting that single-ended output, and if we are second input is connected to that DC supply source. So and this is called a positive feedback if single-ended is this DC supply source, and this is fed back to that input to that second transistor. This is called positive feedback source coupled logic gate, and so this is all about that current mode logic. And so thank you for joining this session, and we will discuss about circuit simulation and device this modeling of circuits by using spice P-spice of cadence in our subsequent lectures. I think that the lecture is scheduled tomorrow at 2 to 3. So thank you once again for joining this session, and I think Chitrakant sir is there. Just a minute. Just a minute. Hold on. हाँ सर कंक्लूड करते हैं. So I hope am I audible now, na? So all the participants, any questions regarding this session? Anyone? So who is having any questions? May raise the hand or put in the chat box. Are you providing any notes in the workshop? When we will get the notes? All the relevant study material we will post on that in the Google Drive, and we will also request to our speakers as well regarding sharing their presentations and study materials. We will try to get that maximum resources or the maximum study materials, and we will provide you. And alternatively, you are having option to go through that video lectures through that YouTube live streaming, and uh, at the end of that this event we will tell you about that study materials and all. And anything else? Anything else? Any questions? Any